Hi, my name is Alena, and today I'll be taking you through question 7 for the spring 2025 midterm. In this question, we'll be going through a variant of the El-Gamal encryption scheme, and it is described here. I'll just jump into the questions, and then we'll dive deeper into each parts of this scheme as we go through the questions. So the first question asks, what goes in the blank in the decryption protocol? So they're talking about this blank here. And so our key for decryption should hopefully be the same key that we used for encryption, which is seen in step 3 of encryption. And we can kind of expand this out because we know that B equals G to the B mod P. So this is actually GBR mod P. And from here, given that this is multiple choice, you can just honestly guess and check for all of these. For example, for B, C1 is C1 is R, and R is G to the R. And then B, as we said before, is like G to the B, but this doesn't really make a lot of sense, and reversing it doesn't really make it better. So B and C are out. D is out because at time of encryption, we won't know what little r is. That is private to the person who encrypted the message. But if you do substitute C1 into A, then we get G to the R B mod P, which is exactly what we want. So the answer for 7.1 is A. 7.2 asks for all the true statements, with A being the variant scheme is IND CPA secure. B is the variant scheme is multiplicative malleable, and then C is the variant scheme is additively malleable, and D is none of the above. So the answer for this question is going to be only A. The intuition behind this is that this scheme is essentially the same as the El-Gamal scheme that we saw in lecture, except in step 4 of encryption, we do symmetric key encryption instead of doing MK mod P. And this MK mod P is what made this scheme malleable, but since we got rid of that from our scheme, now the scheme is no longer malleable. So that's why B and C are not selected. But besides that, El-Gamal is IND CPA secure, and we did not make any changes that should have affected that. So A is the answer. Okay, 7.3. Recall that the El-Gamal scheme from the lecture is defined as we kind of just said. So Alice and Bob believe that this variant scheme will protect them against a man-in-the-middle attack from Mallory, unlike the lecture El-Gamal. Assume that Alice and Bob do not know each other's public keys and must first share them over the insecure channel. So is it true that they are resistant from man-in-the-middle attacks now? And this is not going to be correct. Specifically, it's going to be answer choice D. As we just said, the only thing that we changed is how we encrypt our message, and we didn't change anything about how we actually share the keys. So yeah, that shouldn't change. If you need more information on why in the first place El Gamal is susceptible to man-in-the-middle attacks, I would look at the lecture slides, but I think the main intuition behind this question is that we haven't changed anything here that would make key sharing more secure from man-in-the-middle attacks. Okay, 7.4. The hardness of which cryptographic problems is necessary for the variant scheme to be secure, select all that apply. Okay. So, yeah, we know that this scheme basically makes use of the Diffie-Hellman problem. And then hopefully, building up to Diffie-Hellman, we know that anyone who can break the discrete logarithm problem can also break the Diffie-Hellman problem. So the answers here are going to be A and B. C, RSA is just not really applicable here, so it's not going to be one of the answers. Okay, and now we're on to kind of the final part of this question. So Alice is about to leave on a 1-month-long vacation and wants the central mail server at her office to redirect all her mail to Bob's inbox. However, since she uses encrypted mail, Bob won't be able to read these messages as they were encrypted with Alice's public key. They decide to use this El Gamal variant to help develop a proxy re-encryption system. This system allows transforming ciphertext encrypted by Alice's public key to be encrypted with Bob's public key instead, while keeping the underlying plain text the same. And so, going further into the actual question, so design a proxy re-encryption protocol using the modified El Gamal scheme. That is, design an algorithm to transform a certain ciphertext where C1 is gonna be kind of like the key, and then, it's gonna be this quantity. It's not exactly the key. G to the R mod P. And C2 is going to be the encryption of the actual message using the key. Okay, and then we're going to encrypt M. However, we want to turn this message into some new C prime that when it decrypts, it should decrypt to the original message when decrypted with Bob's private key. So TLDR is that the message is going to get encrypted with Alice's public key, and then we need to do some sort of transformation to it such that when Bob tries to decrypt it with his private key, it should work and it should be the original message that was encrypted. And then, yeah, so V you can think of is going to be this transformation that we can think of, and then we'll need to give the new ciphertext that Bob can use. So if C is the ciphertext after being encrypted, after the message is encrypted by Alice's public key, C prime should be the ciphertext that can be decrypted by Bob. Okay, so let's jump into this problem. So recall from the first part of this question that our key is going to be the hash of C1 to the private key of whoever's using the key, mod P. So when Bob derives the key, when Bob derives the key is going to equal GR, like substituting what C1 is. The key is going to be G to the R B of Bob mod P. However, in order for the encrypted message to successfully decrypt to the original message, we need to apply the key GRB, but B is Alice's private key, mod P. So how can we get from this key that Bob will actually use to kind of transform to Alice's like kind of derived key when we actually apply it to the ciphertext? So we can write this further. So we want our key to be the hash of the new cipher key, or the new ciphertext that B is going to try to decrypt. But when you actually evaluate this after he applies his key on the augmented ciphertext, it should actually just evaluate to the key that we can use on the original ciphertext. Okay, and then this, when we apply it on the original ciphertext, will give us back the original message. Okay, so if we try to figure out what this now C1 prime should be, we should get that it should equal G to the R B of Alice, B the inverse of B of Bob, mod P, right? Because then this will cancel out the Bob's private key and then add in Alice's private key. And this actually pretty much solves our question. Our transformation here is going to be this part. That's basically the crux of the transformation we want to make between the ciphertext, and then this is actually what's going to change for our ciphertext. So V is going to be this transformation we're making. So the answer for what V equals should be A. Our augmented ciphertext, or at least the first block, will be C1 to the V, right? Remember that our original C1 is G to the R, so this is just G to the R times our V, and then C2 can just stay the same, because by definition, we tried to make sure that we defined our C1 so that our key works with the original encryption of the original message with Alice's key. And that pretty much solves this question. Okay, so for the last part of this question, it asks, recall that the original El Gamal scheme from lecture defines C2 as M times B to the R mod P instead of our like encryption scheme. is it possible to create a proxy re-encryption scheme with lecture El Gamal? And the answer here is going to be A, yes, and with the identical setup, because all of the manipulation the intuition behind this is that all of the manipulation that we had to do was with the definition of our key. And how we define our key is the same between this scheme of this variant of El Gamal and lecture El Gamal. Since the only thing we change between the two schemes is like how we actually encrypt, that's totally independent to how we defined our key. And so this whole proxy re-encryption scheme should work exactly the same for both El Gamal schemes. Cool. So that's the end of this question, actually the midterm. So hopefully you're able to get through it, and hopefully this helped.